Hello class. In this video, I'll go over different data prep techniques that we discussed in class, and I will go through an example and show you the prediction difference when you have poor data prep and then we have good data prep. So the two things that I'll go over are essentially transforming a target variable and removing outliers. Okay, so I'm just going to upload the data set here. I'm loading different libraries needed. So this is R. It's a little different than Python. It's more statistical based. And Python's more versatile. It can do a lot more general programming things like create websites and stuff. And this is just more based for stats. So it has some nice visuals and stats packages. It's more based for analysis. It's very similar. It's a programming language. So I upload the data here after I have the packages created. I'm just creating dates to match my economic variables. Don't worry about this. Just data cleaning, removing redundant information, right? This is the variables that we have in the housing data set. So it describes them. A good descriptive stats. We have N, so the number. So alley right here, we can see we don't have a large number of houses that have this alley variable. So this is exactly what I was talking about, filling in the mean, filling in missing values. We would never do it with the mean. In this case, we really couldn't because it's an alley. It's a dummy variable. It's either they have an alley or they don't have an alley. There's different options in this, but essentially you code it as a dummy variable because there's really only two options for this. And that's how we could get these other observations that equal 0. And these 91 would just be 1. That's one way to do it. Or you could label encode it, which isn't really appropriate because the responses aren't to be assumed equally variant. You probably could one-hot encode it, which is just creating dummy variables for each option on alley. But again, these are the important parts of data science if you want to learn it. Here, right, lot frontage. Some houses don't have a lot frontage. Then we can go through the mean, the standard deviation. You have skew here. So the high skew variables, you'd want to transform them. So we look for skew in our variable. And notice that this is I just uploaded this data set, right? So you notice BSMT, unfinished square foot, there's no lowercase here. So I'm very happy with some students, the way they were submitting their homework assignments. They were listening to the way I was talking about variable encoding. As you can see later on, I follow this. See, I'm creating new variables, right? Lowercase BSMT, capital full case, right? Lowercase living for L, for living rather, and then SF square foot. So I follow my own advice. See, and like I said, some don't, but this is a very, very nice, elegant way to name your variables. So going back up to the description, we can just examine all these variables, perform a little bit of manual inspection. And if you're just interested in the sale price, which I am, skew is not too bad. Kurtosis is thickness in the tails. That's essentially the weight of the outliers. So now we can visualize the first floor square foot, right, and sale price. So we get a cube plot. And these are the values here, right? You can see it's kind of like a funnel, a little bit of a funnel here, but this is definitely an outlier. Looks like there's a lot of square foot in this house, but it's a very low house. Potentially it is under construction. It's not finished. It might not be inhabitable. There are many different factors for this. It's probably not a good representation of the population, right? That's why it's an outlier by definition. So we definitely want to remove this, and we might want to remove one of these variables. Yes, you can see the funnel here and the shape. So it's kind of like a line here. You can see it. So I'd say these two are essentially outliers because this has somewhat of a trend, right? It's bunched. It's a funnel, like up here, but it kind of has a shape to it. I try to remove these two values. We'll do that right now. We'll see our prediction error, and then I'll come through the top here and I try to run it without removing it. Hopefully the code, everything will be nice. We'll see. We'll test it out, and then we'll see the prediction difference, including these values. All right, so how do we remove it? We just, in R, it's just minus which variables are greater than 3,000 square foot and less than 300,000 price. So in this case, we do that. Let me also look at it again. All right, it did its job. Now we look at the sale price distribution. Remember I was talking about, ooh, that's not normal distribution. So that could definitely impact our prediction and the stability of our results when we go to predict on new observations. So what do? You want to log it. You would log transform this sale price variable, and instead of being right skewed, right, it'll be more normally distributed. And what I do here is I put log and I train plus the sale price. And when you log a value, if it's zero, so if there's a house price with zero, then it's not able to be logged. It'll have an infinite error, INF. So that's why we just add +1 to every observation. It doesn't really do anything because it's still the same exact transformation. It's going through the same function. So this data is just exact of going through this function. It's the same, right? Whether it's the first data point or the last data point to get through here, it's all getting transformed to the same function. So essentially, that makes it okay, right? In simple terms, I think that's good enough explanation. So let's do it. And then we're going to show the normal distribution now. Boom, there it is. So that's very nice. And now our prediction results will be much more stable. Looks almost exactly like a normal distribution, a nice bell curve. One little caveat though is that our y values, when they predict, they will be log transformed. So our prediction error, we'll have to put it into an exponential function to reverse the log. So that's just a little caveat. Otherwise, your prediction error would look erroneously small. So let's run the prediction here. Hopefully it runs through. This is data cleaning, right? So it's just all label encoding, encoding different variables, right? Transforming them to different levels, factor levels. We want high encode certain variables. Make sure there's no missing values in each data set, and you bind them together that I just created from the dummy variables. All right, now this is the cool part. So we have our data set. Anytime we want our results to be reproducible in research, we always set the same seed. So this will make, when it's creating a data partition that's a random sample, it won't be so random anymore because this is telling the computer to start at a certain seed point, so it's not really random. And this is good because if I pass this into someone else, or if I'm publishing a paper, someone else can verify my work. My work is always reproducible. So this is important in homework exercises when they ask you to set a seed, so that way your results will be what the professor's looking for. So this one I just set 1, 1, 1. And now, right, I create a data partition, I split on data price, and I'm creating a training set with 80% of observations, right? So I have a training index with 80%. Here it is, training set, and then minus the training set, the other 20% will be the test set. And that's what we're going to test our model on. And it's very common in data science. So creating a test set. So we're going to use the XGBoost, very similar. I like this because you're going to see a whole bunch of error rates, and you can see how machine learning, right? The model's learning every time, and the error is getting increasingly smaller. And then it finally has diminishing return where it just flatlines. So that's usually about 600. So I'm not going to do the full 1,000. I'll do like 900 maybe rounds. I don't know, 800. You should be able to see that stop at 800. Let's check it out. It's pretty cool. That's why XGBoost is one of my favorite, and it's also one of the most efficient and most predictive right now. So there it is. That's our RMSE, our residual mean square error. You can see it's decreasing. It stops about 500. So I was a little early. See, it stops increasing with accuracy at about, farther than I thought. So I only need to do about 250 of these because you can see 272. 272, the error, it's completely flatlined. So we're not getting any better. That's just saying that the model is not learning anymore with the data that we have, and it's essentially maxed out its capabilities. So we could run this again with 300. And it's super quick. And now we get to have a cool picture. We started out with a pretty big error, and then the second iteration it learned and said it found out where those errors were coming from, and it just keeps going. And this is the essence in machine learning. It's extremely powerful. It's quick, as you can see, all these iterations, and it would take us a lot of time to manipulate a model and figure out how to get our error down incrementally like this. So take advantage of these resources, machine learning, and all this different compute power that's available now to us that wasn't really available 10 years ago. So we can do an importance matrix for different variable importance. So this would be like showing you what is the most important variable for prediction. It does this by essentially randomly computing or inputting variables for each variable under observation. So total square foot, it's just going to randomly adjust all the rows in total square foot, and it's going to see the difference in error from this efficient model, right? So it's going to notice that when total square foot is random, the error is like the most increased. So that's how it gets that total square foot is most important for this XGBoost. So that's how it calculates it. So total square foot was super important for driving housing prices. The overall quality was, and then other variables, they're really not close to these two. So you have like garage finish, whether there was central air in the house, how many cars the garage had, 1 or 2 car garage, the lot area, so that's like the property, basement quality, thinking of like a man or woman cave. So that's very important. People like kind of have a nice basement to hang out with, watch golf or whatever they do. And same thing, garage square foot. We can go down money and mortgage. Those are the economic variables that I added. So that's my contribution to the literature. A lot of these papers, they don't have any economic variables. So I'm interested in the interplay of microeconomic housing factors and the macroeconomic variables and what the intersection is of these. So here we have money, right? It's a pretty decent increase. It's the M1 money supply in the country. And then we have mortgage rate, which is a pretty good driver of house price, according to this. So it's nothing to do with prediction. That's just additional finding out what features are rather important. And now we're actually running our model on the test set. So here we are, we predict, right? With our test set, we predict, get the results. And this is the RMSE, right? So it's quite a bit larger. This is our training set. And this is exactly why we create a test set. Because the models can memorize, as they are right here. As you can see, they're decreasing quite a bit. It's memorizing all this data, essentially. So we need to know, is this a really efficient model on a new, independent, unseen data set, which proxy as a population that we're interested in stats? So it's a decent error. It's definitely not bad, but it's not as good as the training set. So the training set's always going to have lower error because it cheats, right? It knows the data and it knows the actual Y value. It cannot cheat with this because we have a test set that it has not seen before. It does not know the sale price for these values. So it's actually predicting them because we C minus. We took out sale price from the test set. Its job was to predict. And then we took sale price from the test set and put it back in to results. And then we know the function for RMSE, right? It's just Y minus Y hat. So this would be observation, right? The actual Y value is the observation minus the prediction. So this is what our results would look like. This is it. It's just Y minus Y hat. And then it's calculating it. You can put this in default summary and get a nice R squared value or RMSE. So RMSE here, C is 0.1578. We have to put that into an exponential function, remember, because we logged the Y variable. So our prediction error will be in units of Y, which doesn't really make sense because we're not interested in a log house price. So we exponential it, and it's about 1.17, so it's about $1.17. Now conversely, let's run it again. I try not to go over that. So here we just don't run these codes right here. So we're not going to remove the outliers, and we're not going to log sale price. Shouldn't make a difference because we have everything named the same. See, sale price, sale price. So let's try it out. All right, now we have this different data. It has not log transformed, and it has those two outliers in it. So with just these little variations, we'll see what the model difference is. All right, so that's 119 in actual dollars because remember we didn't log, so we're not going to need to do this exponential. So it's still a little bit larger than our $1. And remember that the test set is usually always larger than the training set, like almost always, because like I said, your training model is essentially cheating. So we're not too worried about importance variables for this, so we just run the prediction. So here we are, we predict. Now we get results, default summary, X. So go over 4 decimal places. So 1, 2, 3, 4. Prediction error, about $31,000. Yikes. Yikes. Not very good. And we don't need to do the exponential because it's in dollar terms. We didn't log it. And the R squared goes down quite a bit. So go the other way, E minus 1, so it would be 0.85. The other one, 0.82 actually. So that just shows you that the R squared value with the percentage of variation is sometimes not a very good proxy of prediction error. So I hope this was informative for you guys. You can really see here, it's quite amazing. So even if we logged this result right here, Yeah, even if we logged it, which makes no sense, it would still be 10. And that would absolutely make no sense because we never um, really logged it. So that's just to show you, even when you're getting the error in logging it, it's a lot larger than doing it the right way. It's quite amazing here. And these just two little things, right? So this is what I'm trying to get you guys to be the most efficient data scientist you guys could be, and to be the best that you can be, because these are the things that it's just taken me almost years to learn. I didn't really understand that this is the whole game right here, right here. It's all data prep right here, data engineering, how to encode your variables, right? How to handle values with high NA, handle variables with high NA values rather, right? And these are just very, very important. This is where you're going to win the battle, as you can tell here. Because if you're quickly going through data prep and then you just throw your model, throw the data into the model, oof, it can be a lot different than methodically going through it, as we saw. So reach out if you have any questions for me. I'm always there. I'm always here to help, answer questions. I appreciate everyone's attention in class for the most part. There's about 4 or 5 students that are really eager to learn. And you guys are pushing me and make me want to, keep giving you these extra little edges that I've learned throughout my years of graduate school and data science. All right, have a nice weekend.